Okay, this is lesson 7 of Unit 1, Infinite Limits and Limits at Infinity. So when we first started talking about limits, and this is even last year in pre-calculus, we had two special situations. And so now we are going to compare and contrast behavior of functions as they approach infinity, as well as when the function tends towards infinity. And I know that sounds kind of like a nuance, but the first idea is as they approach infinity, which means for very, very large x's. And the second part, the part that says tend towards infinity, that means where we have a vertical asymptote, where the function is unbounded. So we're going to connect these two together. So topics 1.14 and 1.15 is connecting infinite limits and vertical asymptotes, and connecting limits at infinity and horizontal asymptotes. So what we're going to do with example 1, we're going to do this through example, is we're going to compare and contrast behaviors involving infinity, and then write down what is the outcome of this. And we're not really going to discover it, we're just going to do it kind of together here. Okay, so we have what looks like a very complicated function for f of x. We have a rational expression. It is quadratic on the numerator and the denominator. So we're going to look at the graph, the first one, the graph as x approaches 4 from the left. So we're going to be tracing the graph towards 4 from the left like that, and we can see that we're headed to infinity. And then as we trace the graph from the right as we head to 4, we can see that we're headed to negative infinity. My infinities aren't looking so good today. Negative infinity. Okay, let's do the same thing with g of x, which is below. So let me move the graph here a little bit. And then when we look at g of x, we're looking at 1 from the left and from the right. So when we look at g of x, what we see is as we approach g of x from the left, as it approaches 1, we're headed to negative infinity. And as we approach 1 from the right, we're headed to positive infinity. So I'll go ahead and write those down. So from the left, we are headed to negative infinity. And from the right, we're headed to positive infinity. Okay, so what is our discovery? Hopefully you can see, looking at the graph and from our left and right hand limits having different values, that f of x has no limit at x equals 4. Because from the left, we're headed to infinity, and from the right, we're headed to negative infinity. And g of x has no limit at x equals 1. And the reason for that is that they both have a vertical asymptote. Okay, so that's where we have an infinite limit. So now let's talk about what happens at infinity. So first, let's do g first, since the picture's right there for us. So the first one, we're looking at what happens when we head towards negative infinity. So on g, it is this way. And so if you notice here, we have a slant asymptote. And that leads us to an unbounded behavior that the function is headed towards negative infinity. And as we go towards positive infinity here, since we're along that slant asymptote, we are headed to positive infinity. Okay, so let's look at the same kind of behavior for f. So let's go up and look at the graph of f. First, as we head towards negative infinity, what we notice is we level off here because of the presence of this horizontal asymptote. And as we head towards positive infinity, we again approach that horizontal asymptote at -2. So we can write those down. So we have -2, -2. So our discovery is the fact that we have a horizontal asymptote for f of x and g of x has a slant asymptote. And since a slant represents a line, and lines have no bounded end behavior, that's why our function g is unbounded at very large x's too, and very small x's. So a limit at infinity is as x approaches positive or negative infinity. That's supposed to be the word the. The limit will approach a horizontal asymptote. I'm going to abbreviate that. That's one thing. Or it will be unbounded. So we have two choices. We either have unbounded behavior or we have a horizontal asymptote. And don't forget that that horizontal asymptote might fall just towards one side. So it could like be bounded by horizontal asymptote for very small x's and be unbounded for very large. That would be like an exponential function. Okay, so now let's talk about this a little more. So in pre-calculus, we learned some basic truths about rational functions. And when the factor cancels out from the denominator, we know that what results is a hole occurs. The graph will look just fine if you're looking on your graphing calculator, but there is a hole there. When the factors don't cancel out from the denominator, a vertical asymptote occurred. Okay, so we're going to use the equations we just did. So there is our f and g, and we're going to find the one-sided limits. So the first one, we're going to do it algebraically. The first limit we're going to do is for f of x, and we're finding it as x approaches 4 from the left. So we want to factor and see if we can cancel any factors. So we're going to rewrite this as the limit as x approaches 4 from the left. And the top factors into -2 times x plus 3 times x minus 2. And the denominator factors into x minus 2 times x minus 4. And as we can see, one of the factors cancels out. So we are left with the limit as x approaches 4 from the left of -2 times x plus 3 over x minus 4. And what we notice is that we didn't cancel out the factor of 4. So what we have to figure out is from the left, where is this headed? So if I use a value like 3.9, what is going to happen here? What I'm going to have in the top is I'm going to end up with a negative number because I'll have 6.9 times a negative number. So that's going to give me a negative number. And on the bottom, I'm going to have 3.9 minus 4, so it'll give me another negative number. So our limit is going to end up being positive infinity. Okay? So let's do the same with 4 from the right. Well, we did all the hard work, so we can just rewrite this as the limit as x approaches 4 from the right. Well, that looks terrible. And our simplified form is negative 2 times x plus 3 over x minus 4. And again, I can't just do a direct substitution, so I want to think about this in terms of what happens if I'm just to the right of 4, like 4.1. What kind of signs will I have? Because I can see it's going to be out-binded, but is it going to infinity or negative infinity? So this is going to lead me to, so I have 4.1 plus 3, so I have 7.1 times a negative number. So that's going to give me a negative over, and then I have 4.1 over minus 4, so that's going to give me a positive number. So I end up with a negative over positive. So that means that my limit is going to equal negative infinity. So that's how you kind of reason it out if you don't have the graph, or you can't really sketch it because you're in a non-calculator section. Okay, let's do the same thing for our g. So let's start by simplifying our rational expression, which the top does not factor, so we really can't. So let's just kind of reason this out. Let's assume that we can see it's going to be unbounded because in the denominator we'll have 2 minus 2, which is a 0. So that isn't going to work. So let's let x equal 0.9 because we're coming from the left of 1. And when we do that, we get 0.81 minus 1.8, so that's a negative, plus 5, which is a lot bigger. So we will have a positive number on the top, and on the bottom, we'll have 1.8 minus 2. That'll give us a negative number on the bottom. So that means that our limit is headed to negative infinity, which is what we saw in the graph. And doing the same thing with the other side limit. So if we do like 1.1, do the same thing. So when we do that, again, that 5 is going to dominate in the numerator regardless of the other two terms because they're going to be relatively small. So we're going to have a plus on the top, positive number on the top. And on the bottom, we're going to have a little more than 2 minus 2, so we're going to have a positive on the bottom. And that's going to give us a limit of infinity, which is what we saw in the graph. It goes along the slant asymptote. Okay, so what that leads us to is the definition and justification of vertical limits. And here's how this works. When you substitute a number in, c, x is c, you have a non-zero number minus 0, so you end up with a number over a number. A number, so we end up with a number over 0, which is undefined, so this becomes a vertical asymptote. That's what C is then. C is a vertical asymptote. And the other case is you have 0 over 0. And again, if they're exactly the same, this is the location of a hole. Okay, so now that we're in calculus, though, we have to use more precise language. So we're going to use our limit definitions to justify a vertical asymptote. So what we say is if the limit as x approaches c from the left of f of x equals positive or negative infinity, or if the limit as x approaches c from the right of the function equals plus or minus infinity, then x equals c is a vertical asymptote. This is a little bit more mathematical way to look at it. Okay, so I'm going to stop here. Let me do this one example first, and then I'll stop, and the second video will be our limits at infinity. So topic 1.13, removing discontinuities, going back to that. That was from section 6. Example 3, use the function below to find any vertical asymptotes that exist. Justify your answer using limits. Okay, so let's simplify our rational expression. So we can turn h of x into, both of these factor, 2x minus 1 times x plus 5, and the denominator factors into x plus 5 times x minus 2. So we can see here we have a common factor. So we get that h of x is 2x minus 1 over x minus 2. So what we can say, x equals 2 is a vertical asymptote since the limit as x approaches 2 from the left of h of x equals negative infinity, and you guys can check me on that, and the limit as x approaches 2 from the right of h of x equals positive infinity. And again, if you're not sure, verify it like we did in when we analytically looked at G. So that would be parts C here and D. And as I said, we'll finish up this section in the next video.